welcome back. So today I have chosen another Leetcode problem that is also a graph problem. It is 2737 Leetcode problem. Find the closest marked node. So it is a graph problem. I'll just quickly go through the problem. So we are given a graph, basically all the nodes with their adjacent neighbors and weight on them. It's a weighted graph. That's the important thing to note. And secondly, we are given a source node from where we have to start, and we are given a list of marked nodes. So we have to find the shortest distance from the source node to any of the marked nodes. So if I go through this example, so here in this graph, this is whole the nodes and their weighted graph. I'll explain with this first subarray. So this is 0, comma 1. So it means there is an edge from 0 node to 1 node and the weight on that edge is 1. Similarly, 1, comma 2, comma 3, there is an edge from 1 node to 2 node with the weight on 3. That is this node. So this is like whole 4 edges on them. And we are given a source node as s is equal to 0. So this is 0 is our starting node, and we'll be given the marked list of marked nodes. So the marked node are 2 or 3. So basically from node 0 we have to find the distance to the node 2 or the node 3. Whatever is the lowest, we have to return that. So let's calculate the distance from node 0 to node 2. It is 1 plus 3, 4. On the other hand side, from node 0 to node 3, it is also 4. So we'll return 4. So that is in the nutshell. I'll also walk through one more example to clarify the problem. So here the graph is constructed from the all the like edge coast and all. So here the source node is 1 and the mark node is 0 or 4. So basically we have to from this one node we can either go to 0th node or we can either go to 4th node. We have to find either shortest cost in either of them. So let's try to go from node 1 to node 0. Can we go here? No, we cannot go. It's like infinity. So let's try to go from node 1 to node 4. 1, 1 plus 2, 3. So 3. We have to return. So what is the minimum from infinity and 3? It's 3. So we'll return 3. So that is. So if in case the distance to all the nodes in infinity, then we'll return minus 1 as written in the constraints. Okay, the parameters we are given n, that is number of nodes, and the edges in row form, and source node and list of basically array of integers of marked nodes. So we have to make it a little bit in structured way. It's not structured. Let's try to firstly construct adjacency list for from the edges parameter. One thing, like it's like weighted graph, so we need to have extra weight. So rather than creating list and int and all that, I'm gonna create one dt object with the class node. So if it's a my neighbor, or I can say just neighbor, whatever we can name it whatever we like, and it definitely it will have distance, and also it will be index. We'll also create constructor distance named index this task distance is equal to distance. Okay, so this is created. Now let's try to create our let me try to do it a little more so that I'm visible. Okay, so firstly I should create a map. So to create adjacency list, and every node can have list of neighbor. That's why we have created the dt object, and after that it will be adjacency list is equal to new hash map. Very good. So I'll traverse through this list of edges. So now list of okay. So in I is equal to 0, I less than, say as list is a part of collection interface, so I can use size method. And by default, I know the inner will be having just three elements, so I don't need to go through that. So what I will do is agency list dot compute. If I like to use this method a lot because this is nice. So I'll give. So firstly, I need to have a list of that. Let's say list dot um, dot get. No, like this. Okay, let's go slow. So firstly, by this, I'll be having the whole list, and from there inside, if I need the first element, I'll be having get of 0. Okay, so this will be my for sure. Okay, so this will be my node which we are targeting, and then new array list. Then we'll be adding new neighbor. Here we'll be using our constructor. Then one will be our node distance. Basically, first is the distance. So rather than distance, I'm gonna change it to index and this to distance. And then I'm gonna go to. So this will create adjacency list in a very good structure. Okay, so our graph is created. So now I'll also take a set and put all the marked node, and marked is already taken variable. So I'll take variable mark for and I marked mark dot add of I. So basically all the marked variable I'm creating in this. So set is created, list is created, and now let's start the. For Dijkstra, we need a priority queue. Just thinking that instead of creating, we need also a node just to store the distance and that. Just to avoid redundancy, we can just, rather than this neighbor, we can just make this as a node just to make it generic so that we can use it at both places. Like we can just use neighbor as well, but I like to name my variables in a good way. Okay, so I think it will be node then queue is equal to new priority queue. Then here it'll be our function tuck, tuck, and this. So let's say this is A and B. So we have two A and B nodes. So it should what should be distance should be less, right? A distance. Okay, and we also have to create a visited node, visited set basically. So in my queue, I'm adding new node, and my distance from the root is 0 and its index is S, right? Okay, and while I'm just trying to run my Dijkstra here, so it will be node temp is equal to q dot board. Okay, okay, and whenever I'm popping it up, then I'll be adding it in the visited. list. So there are always two methods. Either you mark it visited when you polling or when you are pushing in the queue. I like to check and the visited and all that when I am popping from the or polling from the queue. So if if my temp if my visited dot contains temp dot index, I'm gonna continue. Otherwise, I'm gonna add visited dot add temp dot index. I'll be using this temp dot index a lot of time, so I'm just marking it as I, just to avoid repeating typing. Perfect. So I have to also add its adjacency list. What are the all possible neighbors? So what I will do to get of I, if I, it can be, it doesn't have any neighbor, then in that case, oh, this will be list of, need to also change here. I feel the question like a graph and all, they're lengthy. They're not very difficult, but they're very lengthy. That is one of the thing I can agree with the most of the students. Neighbors is equal to adjacency list dot get. So if neighbors is null, then I can just continue. Otherwise, what I'm gonna do, I'm gonna node n, it will be from neighbors. Okay. So I'll be just inserting in the queue. If visited dot visited dot contains n dot index, if it doesn't contain, if it doesn't contain the n dot index, then I'll add, you can say q dot add new node, and also what I'll be adding, I have to add distance plus index, so that will be n dot index, and my distance will be n dot distance plus whatever the distance was for the I dot distance. So so here we have to also check if it is in the visited, right? If mark dot contains I, then we'll return I dot distance. But if we reached at the end and we are not able to find anything, then we'll return -1 because we don't have the reachability of that node. Let's try to see how much close we are. I think we are quite close. I all distance. Oh, it's temp dot distance basically. It is saying n is already defined. Yeah, it will be temp dot distance. Where is n defined? I'm not sure. Minimum distance. Oh, okay. We cannot use this, but I can use n1 then just to make it little clear n1 and n1. I think they should begin. Actually, n is already there in the parameters, so that's why we cannot use it. So it should have been 4, but I returned -4. There is some problem. Let's try to do that again. One optimization we can do, like if the distance measured is more than what is already found, we don't have to take that node inside. That is optimization. But it should work. Why it didn't work? 2 or 3. We should have reached there, right? Let me try to debug. This is node. Very good. This is known as priority will be on the basis of the distance and new node. Firstly, index then distance. Oh, maybe we have to do here s comma 0. Still, it's showing me the same result. No benefit. That's okay. So, firstly, it is taking index then distance. Yeah, I told you I have created some problem. Actually, I thought something else, then I changed in the end. That is creating the whole problem. Is there anywhere else we are creating the same node? Yeah, I think the test cases are passing. Let's try to submit. I don't know if it will be passing. Yeah, it is accepted. Oh, beats 100%. That's amazing. Oh, I think they have just posted this question yesterday, so that's why it doesn't have much more. So one thing we can like optimize this a little bit. I just want to discuss with you how we can do optimization. Here we are, we can do optimization here till this point. Like we are adding this, we are adding a node. We're just checking its visibility or not. We are just adding it again and again in our you can say queue. We can little bit do optimization. I won't say a lot, but let me try to do. Let's say I took distance is equal to new and for distance of s will be 0 and for after that for int I is equal to 0. This is basically I'm trying to do optimization, see how good it is. For distance is equal to we have to just take extra space of like n, and let's see how much. It's experiment I'm doing, man. And it will be n, then I plus plus, then after that distance of s should be integer dot max value. Yeah, that's amazing. And whenever we are marking that node as visited, then will be d of I is equal to temp dot distance. That is fixed, and we'll be calculating here or I always try to use De Morgan's law. So basically here, if this is visited, I'm gonna do this. You can say here, remove this from here and continue, and or basically the distance which you have found is higher, like basically this distance. This is either higher than, like should be higher, because equal to might be fine. Equal to should also be fine. Less greater than equal to d of n1. Then we don't want to take that route. Let me try to see if this runs. And I want to see basically the time, if the time changed or not. Node cannot be converted to end. It's the problem. And one dot distance, temp dot distance. This is integer, but this is integer. So, and one dot mix. So here I'm submitting. Let's try to see the optimization. How much is the difference? We'll try to compare both the things. So the optimization took 13 milliseconds, and let's see the first one. And the first one also took 13 milliseconds. Maybe the test cases are not a lot. Yeah, how to see how many test cases there are? I'll try to see if I can see that. So basically, I think, but it was a good optimization. Like if you have a large like files and large test cases, you don't want to add something in the queue again and again. So that will be a good option. But yeah, I think this was a good question, and I liked it. I like graph. The only problem with the graph problem is they are very lengthy. You have to like do write a very large code. You firstly have to build them. You have to practice them. That is the thing that you have to see. Other than that, I think they are nice. They are kind of nice. They are good. Okay, thank you. Thanks a lot. I think it was really nice doing this question again, and I'll be back very soon. Bye.